it's what I call Wonderland of Landslides.
You're listening to The Cosmic Cast. Hello, and welcome back to another episode of The Cosmic Cast, brought to you from the Earth and Solar System team at the University of Manchester. I'm John Fisher, and we have the usual co-host selection of Marissa Lowe.
Hello.
Ricky Bahir is over there.
Hello.
And Tom Harvey is just below me.
Hello.
Proverbially. And, of course, we're joined this week by an extra special guest, Giulia Magnarini.
Oh, good. Thank you for having me.
No, it's a pleasure. So you're a PhD student based at UCL at the moment.
Yes.
So your project is all about, if I'm correct, it's all about flow, debris and avalanches and things like that.
It's more focused on a specific type of landslide,
okay,
which are called long run out landslides, and these are hypermobile type of landslide, which means they extend for distances that nobody would expect from, let's say, classical frictional model.
Okay.
And so the reason why, so the mechanisms are not totally fully understood.
I guess I forgot to mention at the top then, so these are specifically landslides on places like the moon and Mars.
Well, yes, but actually they are found pretty much everywhere in the solar system, or for, let's say, the places where we have images from. So Mars, on the moon, and on our planet, the Earth, but also have been spotted on Ceres or Iapetus, which is a moon of Saturn, and I'm pretty sure, on Mercury as well. Yes, pretty sure if we send spacecraft somewhere else, we would be able to find them. I wish I could spot one on Pluto, I have to say.
That's cool. I didn't realize they were so widespread amongst the solar system then. So that's really cool. So what are the sort of driving mechanisms then? It's not necessarily tectonism or something.
Yeah, that's the big question about this type of landslide, understanding their behavior. So not only they extend for so many, well, when I say for so many kilometers, is, let's say, relatively to their vertical height. So at the elevation at which they, fall onto the valley floor. So let's say their horizontal extent is many, 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 many times more than the vertical drop. And so the mechanism that allows so it's not really understood. And actually they are found like moving with very high velocity. And so, one may think, okay, if they collapse from very steep and high slope, there's a lot of potential energy involved. But when you do the calculation, then the run out must respond to something else that is not just, transforming potential energy into, kinetic energy. There's something more happening that is not really understood. So many hypotheses have been proposed to explain this behavior. And it can involve fluidification of the entire landslide mass. So through, presence of water, which is, commonly found on our planet because our planet is rich in water. But some others are suggesting even like fine-grained materials may be able to behave like a fluid, so being able to fluidize the mass. But some other mechanisms propose some sort of reduction of friction instead at the basal layer, where the slide move over the valley floor. And so let's say maybe there was ice, so providing a slippery surface, so reducing friction. Or some other mineralogy like clay minerals. And so through frictional heating may be driving dehydration of these hydrated minerals, and so creating a sort of watery film, like a very thin layer, favoring low friction. And many others. Could be even like decarbonization of carbonate in case, or dolomite mineralogy, which might be a bit unlikely to find on Mars. But also all these mechanisms are kind of plausible, at the same time wouldn't be able to explain landslide in, so widespread in the solar system. So it seems there's no an environmental link, if we want to say, we know that the moon is without an atmosphere, and likely ice was not present at any stage of the geological history of the moon. So either there's a more fundamental mechanism we still don't understand, or there are many, let's say, way of, let's say, producing this hypermobile type of landslides.
Yeah.
So when you said that the equations that you put them into, it doesn't seem to make sense how far they run out.
Yeah.
Is there any correlation between how much they deviate? So you always see that they deviate by a certain amount, or is it almost random as well? You just know that they go further than they should, but there's no commonality.
Yes. Okay, so long run out landslides are characterized by what is called in the literature HL ratio, where H is the vertical drop and L is the horizontal length. So they are characterized by a HL ratio, which is below 0.6, which is let's say a number in the classical theory of friction. So what in the literature you can find is that it seems to be a correlation between the HL ratio of landslide and their own volume. So the bigger the volume, the smaller is this ratio. What I should actually say, this ratio is somehow used to represent the mobility of this landslide. So the smaller is this ratio, the more mobile are these landslides.
The further they go, I guess.
Yes.
Yeah.
The farther they extend, obviously compared to their vertical drop. And so it seems to be a link with the volume. So the higher the volume, higher the mobility. But yeah.
So I remember I visited a landslide deposit up at Ingleborough, a bit up north near Lancaster, a couple of years ago. And yeah, picturing that, it's a very steep hill. And I suppose that's sort of the image we'd have of a landslide. You'd picture a steep hill, maybe like on the coast or something, and you'd imagine that collapsing. And I suppose in your head, you can kind of see, oh yeah, if the slope is that steep, you can see why that would cause material to slump down or slide down in some way. But I guess it's harder to imagine such shallow slopes causing such huge landslides.
Yeah.
Are there any places, like other places on Earth? I'm thinking maybe if we're introducing water into it, are there any other places that might be better analogues for these planetary landslides?
So I used a terrestrial analog, which not unfortunately, I had to travel to Chile. I would say, there was not in UK. So I traveled twice to Chile, and we're in the north part of the Atacama region by the coast. So you have this really nice coastal scarp, which is like a cliff about 700, 800 meter high on the coastal plain, just in front of the sea, a few kilometers away from the ocean. And so from these slopes, there are evidence for long run out landslide, and especially one well preserved because of the hyperaridity of the area. So it makes things easier to be preserved. And so to actually work on the morphology of this deposit. And so so that's one thing of my project I didn't mention. I work on Mars, Moon, and the Earth, and so the Earth on it's a great place, also because then you can travel, you can visit places, and you can see with your eyes, touch with your hand what you are working on. But it's an active planet, and so we have erosion going on, plate tectonic, so all these factors that tend to obliterate pretty quickly in geological terms morphological evidence for any processes, but in my case of this landslide. And so I have been using then images from Mars or the Moon. From we have nowadays the latest mission are providing incredible high resolution images, and I go down to 50 centimeters per pixel resolution, and so a lot can be done on the morphology of this landslide, even if they're so far away places. A lot can be done that actually cannot be done on our planet. Sounds a bit like absurd, but that's how it is sometimes.
So obviously for the Earth, people can point out to you, there's been this giant landslide in Chile, go look at it. For the Moon and Mars, did you have to go through images and look for the...
So for Mars, it's somehow easy. There are already other people who have worked on that. And actually, long-run landslide have been one of the first, let's say, geomorphological features, geological features that have been identified from very early missions from Mars. If I'm not wrong, might be the Viking mission, if not even earlier. No. Because they are big. And so even with low resolution images provided by the mission at that time, it's so easy to spot them. And Valles Marineris, so this long scar in the Martian lithosphere, like thousands of kilometers long. It's what I call Wonderland of Landslides. It's it's this canyon with really steep wall, up to 8-9 kilometers at places. And so you can imagine, how can easily things at some point can become unstable and just fall. And in some part of Valles Marineris, the entire valley has been like obstructed by this deposit. And in some other, not entirely, you can identify, in individual deposits, in some cases one on top of each other, and are beautifully preserved. When it comes to the Moon, so same thing. That actually just one, at least so far that we know about, long-run landslide that looks very similar to Martian landslide, and it's at the far side of the Moon, at the Zielkowski Crater. So this landslide probably developed from the crater rim collapse, but outward. It usually happens inward, so within the crater, but in this case, outward. And it's, again, we are talking about 50 kilometers long landslide deposit. But then there is a second case, which enter in the category of long-run landslide for the H/L ratio we mentioned before. And it's at the Apollo 17 landing site area, the Taurus-Littrow Valley. And, the Apollo 17 mission had the only geologist who walked on the Moon, Harrison Schmitt. And so he explored the deposit of this landslide, obviously, conducting many other activities. But that's somehow the reason why my project exists. He came up with the idea, he contacted other people, blah, 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 and decided to have a project on long-run landslides, thought that we could also look at the Apollo 17 landslide, and is actually one of my supervisor now.
That's
So
very cool.
I was like, okay,
Mm.
yeah. When I saw the adverts, I was never really a big fan of landslide, if I can be honest. But I thought, okay, these are really big things. They sound exciting. Okay, and then I thought, okay, it would be actually maybe chatting with an astronaut about his experience.
Has he
Something
had
that-
lots of input to the project?
We had some exchange of emails, so we had some discussion. My initial, let's say, 2 years, I mainly focused on the Martian landslide. I was more, let's say, familiar with Martian data sets, and so I studied from there. And then I went to do field work, and so on my halfway through my second year, I started then working on the lunar landslide. And so there we had a bit more interaction in discussing the morphologies. And I actually found myself writing an email to him, and I was a bit intimidated, by the person he actually is, the idea he walked on the moon. And I was like texting him saying, I'm thinking about this and this and that, and I observed these morphologies. When you were there on the moon, did you see this type of morphology, or and I was thinking when I was typing, I'm like, I'm really texting it, this sounds so like sci-fi. I'm asking someone who went to the moon if he saw these morphologies on the moon. Anyway, it's kind of, yeah.
that's
That is
so cool.
insane.
It's cool.
It's not like, did you see them in those images?
Yeah.
Do you remember seeing it when you were there?
Yeah.
Oh.
So
That's
yeah.
a very unique experience. So as you're working on Apollo 17, then do you get to look at some of the samples that they collected? Are they relevant, or is it literally just thinking about images and field observations?
Yeah, so this is actually somehow a side project that does not belong to my original PhD project. And yes, so I will be looking at XCT scanning of core sample tubes that have been collected from the landslide deposit during the Apollo 17 mission in 1972. And they have been brought back to Earth. But NASA had somehow the idea back then to preserve some of the materials from Apollo mission. So it's not just the 17, I think it's also from Apollo 15 and 16, to keep some of these samples, store them safely for 50 years, which is now, with the idea of then studying this sample when more advanced technology would be available, and so to actually get even more science out of this extraordinary program that was the Apollo. And so yes, so I will be looking at XCT scanning of the sample taken from the landslide deposit with the aim of studying in 3D the structures of this deposit. So observing the grain size of the debris, and if there are any structures that can have some provide some hint to the emplacement mechanism of the landslide. And yeah, and so extracting this type of information. And yeah, so unfortunately it's not started yet, so I still have no access to these images. So I'm kind of looking forward to. And so hopefully I will be able to have even some preliminary observation, maybe result to then present next year to LPSC.
That's really cool though. So you're going to be like one of the first people to see like this brand new data that comes from the moon, effectively.
I have to say, there are other people who are actually already working on this sample. on the mineralogy and obviously sieving, so preparing. But yeah, I actually have been, when I actually think about that, I really feel more than privileged at the idea of being part of, these next generation of, or well, I say current generation of scientists who are looking at sample 50 years old.
Yeah, that's
I
really
feel
cool.
like I've done my PhD wrong. I'm not supervised by an astronaut, and I don't get to open new moon rocks. What have I done?
Yeah, what are you doing with your PhD,
Yeah.
Marissa, really?
Oh no, I've done it wrong. I didn't know that was the option instead. So, Julia, it would be great to see some of the landslides that we've been talking about, because one of the things that I usually remember from seeing you at conferences and things are these gorgeous digital elevation models that you usually have on your posters and in your presentations. So, yeah, it'd be great to hear more about the data you use to make these, and yeah, what you do with that to make these elevation models.
So maybe I can share my screen.
By the power of editing, I'll just do this and we'll cut straight to the pictures.
So this is my Martian case study in Coprate Casma, which is a area in Valles Marineris. And I annotated here this famous H ratio. So H would be the vertical drop of the landslide. So how many kilometers collapse? It's actually 5 kilometers. And it extends for 63. So measure from top to the toe horizontally.
So I mean that's huge.
This may seem like a sorry. Go on, John.
I was just going to say, so a 5 kilometer cliff that's then producing a landslide of 6. That's almost unimaginable, isn't it? I mean, to put that into context, I mean, like 63 kilometers. I mean, that's like, Liverpool is only like what 30 odd miles away from Manchester. So I mean, that's mad, isn't it?
If you for someone maybe familiar with London, if you think about the M25, you can actually take this landslide and put it inside the M25, and it will fit.
Wow.
And if you think about the volume on average, so imagine you are standing in London below an average of 300 maybe meters thick deposit. So it's pretty impressive.
That is very impressive. Yeah. So it'd be good just to take a moment then to sort of think about what we're looking at here exactly. So I mean, these are sort of artificially constructed images almost, aren't they? So I guess this is what's called a DEM, or a digital elevation model.
Yes. So to create this type of product, I take images, high resolution images from CTX camera, the context camera on board the NASA mission Mars Reconnaissance Orbiter.
Yeah.
And so these images have a resolution of about 6 meters per pixel. And so what I have to is trying to find 2 overlapping images, and using elevation data obtained from another instrument on another NASA mission. The instrument is called Mars Orbiter Laser Altimeter, which provided, I think, from 1999 to 2001 elevation data of Mars. So by combining the high resolution images of the current mission plus the elevation data, combining this within a photogrammetry software, you can have commercial photogrammetry software. I'm pretty sure I can mention the name. It's called Socket Set. And
they're a sponsor of the podcast, don't worry.
Okay. Or you can use some other like free, let's say, software. I think is the Ames pipeline to actually being able to produce this digital elevation model. So let's
So,
say
so
then,
how long would it take you to produce one of these?
so, okay, what we are looking here is actually the combination of three image pairs. So let's say for each pair, we are talking about, I would say a working day, if we consider a working day, maybe 4 or 5 hours, let's say half working day.
Yeah.
It's just accounting for coffee breaks and scientific discussion.
Love it. Yeah.
Or let's say desk work. No, I'm joking. And yeah, I would say so. Obviously, the bigger, CTX images come also with different sizes, depending on, let's say, the photo shoot. And so the bigger the images, the longer the process will take. But yeah, I would say that, in this case, a good 2 working days, for obtain everything, because sometimes the process doesn't work right at the very, first time. You can actually manually, if you want, you can try to, modify some parameters of the, let's say, default setting that will produce your DM. So once you produce your digital elevation model, which is then, yes, the 3D version of your terrain that you're looking at from optical images. So you give volume to your 2D image, and then you also produce what is called an ortho image. So it's when you take a photo with whatever camera, even our camera, you have the center of your image is somehow the only point that is perpendicular to your lens, let's say, if not just the only point, but the area around. And moving towards the edges of an image, then you have some distortion. And so this distortion, when it comes to, conducting research that requires measuring things, then it's not okay. So then you need what is called an ortho image, which is an image that at every point, even at the border, it's like looking perpendicular down to the surface. And so this oblique view is then generated by using a digital elevation model and overlapping an orthophoto onto a digital elevation model. And so you can have like a realistic view of this gigantic landslide. Yeah.
So once you produced something like this, what I guess the questions are, what measurements do you take, and what's the intentions of taking those measurements? What are you trying to find out?
Yeah, so I focused my entire PhD looking at these linear features that you see marking the surface of this landslide deposit. And this is like a alternation of ridges and trough. And it's this type of morphologies is somehow common to long run out landslide. And so so I've been spending time measuring the distance between these ridges, and also how the distance between these ridges change throughout the length of the deposit. And so that was the, let's say, quantitative part of my research, on top of calculating the thickness of the landslide at different point of the deposit. And so
how would you calculate the thickness?
All right, so to calculate the thickness of the landslide, obviously you need the basal surface on which the landslide is resting on now. And obviously we cannot see that. So we need to infer it. So the process maybe will have some, will have some error, the final value of the thickness, you need to take into account the, the error that might comes with. But what we can do is, if you have then a digital elevation model, so you have elevation data for what is around your landslide deposit, okay, you can then interpolate the surface around your landslide deposit. Then you can get an estimation of the surface underneath your landslide. And so you can use that to then calculate thickness you can use it to calculate the volume, and then if you are interested in specific places of your landslide deposit, then you can estimate the thickness. And so what actually the result from this type of analysis I did, so I so that the distance between the ridges actually change with the thickness. So there's a scaling relationship between these two parameters, and it was interesting. So the distance between the ridges is consistently 2 to 3 times the thickness of the deposit. So so
it's a direct correlation between them then.
Yes. And so this actually was the first time that was, let's say, found in natural landslide. This type of correlation was found previously in laboratory experiments on rapid granular flow. And so, my idea, it was like, okay, we have this landslide with incredibly preserved morphology. And so we did try to see whether the scaling relationship actually occur, let's say, outside the lab. And so that's the type of morphological analysis I also did for the terrestrial landslide and the lunar landslide, the Zielkowski landslide.
And did you find a similar relationship then?
Yes, the result all fit this relationship of the distance being 2 to 3 times the thickness of the deposit. Obviously, there are margin, error bars that you need to place on your point in your plot, and due to as I said, the uncertainties linked to thickness estimation in the first place, that it might be the, let's say, primary source of uncertainties for the ratio. But even after that, the result seems really being consistent anyway within this range. So
that implies it's a relationship that's independent of composition then as well.
Yes, so it's independent of composition because we find it on 3 different planetary bodies and so diverse, one from the other, and also the scaling relationship was found in the lab. So it looks like there's a mechanism behind that is scale independent and, let's say, if we want to use environmental independence. So it might not be linked necessarily to the presence of any specific type of basal surface. Someone has proposed ice, because actually this type of morphologies, these longitudinal morphologies, are commonly observed in terrestrial landslide and placed on glaciers. And so this morphological similarity has been often used to, let's say, somehow infer the presence of ice on Mars rather than infer, let's say, putting out there this possibility. And
so I guess if you see it on Earth, then that sort of almost rules out gravity effects as well.
Yes, so that's another thing that obviously, you think in the first place, okay, how gravity affect these processes. And when I studied my PhD, digging into the literature, I couldn't find anything from anyone who actually was able to, somehow understand what is the role of gravity into this type of landsliding processes. But yeah, obviously for this longitudinal morphologies also, it doesn't seem that also gravity plays a role. Yeah.
Amazing. So I believe you published a paper on all of these results as well, on the longitudinal ridges.
Yeah, hopefully at some point, many papers on. But yeah, so
First of many.
so we published a first paper on this Martian landslide, which was my first case study. So we published, and so I'm preparing, actually I submitted now a second manuscript on the Chilean landslide, and I'm preparing a third manuscript then on the lunar landslide. So kind of having sort of, I call it a trilogy, the fellowship of the ridges, but kind of give us a sense of,
Well, I hope that's what the titles of the papers are called.
Yes, volume 1 or part 1. Yeah.
So do you think, I don't know if this is the intention of your studies, but do you feel like from what you found, you are any closer to understanding why they are so odd?
I don't think I don't think I'm contributing enough to say I'm advancing the knowledge of them. But I think the idea behind this approach of focusing on morphological features, the idea that some processes cause them. And so if we understand what is causing these morphologies, then it can help maybe either better constrain or rule out some other processes that are involved into the formation of long run-out landslide.
Yeah, I mean, it seems like quite a fundamental thing to understand to me, really.
Yeah, and so obviously we, in the lab experiments I mentioned earlier about rapid granular flow, they obviously were able to, observe what was happening in these very thin flows. And it's basically a mechanical instability that is generating within the flow due to the high speed and interaction with like a rough surface. And so this interaction creates this instability that then creates helicoidal cells within the flow. So obviously the difficult part is then moving, let's say, lab observation to field scale observation. And we kind of suggest that maybe similar mechanisms are involved in the formation of these morphologies of Mars. But then what we did in Chile for the terrestrial landslide, so we had access to some outcrops, and some of these outcrops were actually cutting through like a transversal cut of a ridge. So we tried to look at the internal structures and see how they correlate with the morphology. And somehow we couldn't find any evidence, for this type of helicoidal, let's say, convection mode proposed or observed in the labs, and then that we proposed for Mars. So we couldn't really confirm. So what we observe can be actually generated by other type of mechanisms like internal folding, and kind of now at the stage of, writing my discussion for the thesis. And this is actually kind of still in the process of interpreting this observation in a, wider implication for long-run landslide mechanism. And
Right. Well, thank you for showing us that beautiful digital elevation model.
Yes.
I hope
Very
so
jealous.
cool.
I wish I could.
no, but I mean,
sorry. We do have one final question for you, which is completely nothing related to do to your PhD. If you could be doing something else completely different, that wasn't working with a retired NASA astronaut, what would you want to do instead?
I don't know at the moment, but I always wanted, actually, in my teenager years, I wanted to become like a park ranger. So I could actually maybe, given also this situation of lockdown, and so outdoor deprivation, maybe I would go for an outdoor job like park ranger, or you stay in nature, kind of try to preserve the environment from bad things.
Yeah,
You
I
can
mean, that's
try
probably a fantastic job to have, isn't it? It must be wonderful just to be like constantly like out and about doing stuff. Yeah, that's really cool.
Yeah.
Is there a particular park that you would like to be a park ranger of?
Well, I really love, I have to say, desert environment, which like, okay, you don't have any vegetation there, but I fell in love with the Death Valley, and it's a natural park. Otherwise I love like forest environment, like Canada, latitude Canada, Finland, those latitude up there. It's really peaceful.
It'd never work out though. You'd one day stumble across a debris avalanche and you're like, oh wait, I'm doing the wrong thing. I need to be a planetary scientist.
I can save you all from catastrophic landslides.
Cool, brilliant. Julia, thanks very much. That sounds awesome. And we'll put a link to your paper down in the description of this episode if you want to check that out. Thank you so much. But in the meantime, for all you in the audience, if you would like some more Earth and Solar System content, we're all over social media, left, right, and centre, from the Instagrams, the Facebooks, and of course the famous Twitter. You can find us there at Earth Solar System and at Cosmic Cast. I think that's right, isn't it? It's at Cosmic Cast, isn't it? But anyway, in the meantime, see you all next week.